Recording. So hello
I
everyone
don't know.
and welcome to week number 10. Oh my god, week 10. This is crazy. We're almost done. This is lecture number 18 and we are finishing up variability and going to move on to the next chapter today. So we first started talking about range and then we said range sucks, so let's not do that one. Then we went to the IQR, the interquartile range, which is very important. Then we did the MAD, the mean absolute deviation, which isn't really important in the grand scheme of things. It's more, its importance is really more of a stepping stone toward the standard deviation, which I think we got this far at least, correct? We talked about the standard deviation. We actually, did we do this page? Did we complete it? Yeah, we did. We got it. Okay. We talked about dividing by n minus 1 in terms of this thing called bias. Did we do this page yet?
No, we're right here.
No, we're right there.
Okay, so let's go here. So Jade had a mean test score of 69 and Jason had a mean of 76. Jade's scores are given there. Jason's scores are given there. So the question is, which student has test scores that vary more from their mean? So if you look at Jade, 20 is very far from 69 in the grand scheme of things, as is 95 really. In the case of Jason, all of the scores are very close to 76. So just by looking, it's almost intuitively obvious that Jade's scores vary more than Jason's if we look at their distance from the mean. But let's actually compute each of their standard deviations using the formulas. So for Jade, we'll make a table for this. So this will be the Jade table. And for the J, what we're going to do is we're going to first compute how far each number is from the mean. So how far is 20 from the mean? It is 49 away. Specifically, it is 49 below. So the deviation is negative 49. How far is 65 from the mean? It is 4 below, so negative 4. How far is 80 from the mean? It is 11 above. How far is 85 from the mean? It is 16 above. And how far is 95 from the mean is 26 above. So those are what are called the deviations. Those are Jade's deviations. Notice, by the way, that if you add up the deviations, you're going to get 0. If you add up the deviations, you get 0. That's always true. It can be proven that the deviations always add to 0. So we're not going to add them. What we're going to do is we're going to square them and then add. So the first thing I do is I take negative 49 and I square it. And that gives me 2401. 4 squared is 16, 11 squared is 121, 16 squared is 256, and 26 squared is 676. So we add up those numbers. 2401 plus 16 plus 121 plus 256 plus 676 gives me 3470. And then I divide 3470 by what number? 4.
5. Oh.
Not 5. Remember the formula. You divide
Oh, minus the 1. Okay.
So then we do 3470. And we divide by the number of data points minus 1. So we divide by 4. And then finally, we take it and we square root it. So 3470 divided by 4 is 867.5. And then I get a square root. And I get a deviation of about 29.5. So that is my standard deviation for Jade. If I do Jason, I'm going a little quicker rather than having you guys walk me through it, only because the other class is a whole chapter ahead because we missed a day. It's not your fault. It's my fault. We missed a day. And I want to try to catch up. So what was Jade's? Jade's was 76, I believe. So 73 is 3 less, 74 is 2 less, 75 is 1 less, 78 is 2 more, and 80 is 4 more. And as you can see here again, like the last one, we see that they do the deviations. If you add them up, they add to 0. So we don't add up the deviations. Instead, we square them. We get 9, 4, 1, 4, and 16 for a total of how much? 34. So if I then take 34 and I divide by 4 and square root it, I get a much smaller deviation of 2.9 or 2.92. You can trust me on the math, even though you can't trust me on anything else, Yesenia. Oh. Does that make sense, everyone?
Professor?
Yes.
I just want to be clear on something. If it's 76, right, and then you had to subtract 73, the reason why it's negative is because you're going down, right?
Yeah, so it's data point minus mean. So it's 73
Okay.
minus 76. 74
So if it was any number above 76, it would be positive, right?
As they are.
This is for this example.
Yeah, but for any example, same thing here.
Okay.
Right? Same thing there. Okay. So here are three distributions, A, B, and C. Each distribution below has roughly the same mean and range. Remember what the range is, largest minus smallest. So 6 minus 1, 6 minus 1, 6 minus 1. They all have roughly the same mean. The mean is the center, the balance point, if you were to try to tip it, right? So they all have roughly the same center. By the way, what is the mean? Based upon these pictures, if you had to give a number to the mean, what would it be approximately?
$200?
200.
5.
5
Oh, we're looking at the bottom. Sorry,
Are
5.
you saying the data point is here?
and minus
What?
1, you said?
No, I said, what's the mean?
Oh.
The mean is the balance point. Where would I put my finger to balance this?
Okay.
Right
Right.
around 3.75.
Okay, so I'm going to go with 3.6. But again, it's an approximation. The reason I picked 3.6 is because 3.5 is right in the center. It looks to be a little heavier on the right side. This one's a little taller. This one's a little taller. This one's a little taller. So it tilted a little bit to the right. Same thing here. 3.5 is in the middle. This one's taller. This one's taller. This one's taller. So it shifts a little bit to the right. Again, it's only an approximation. What's the range? The range is about 5. All right, 6 minus 1, 6 minus 1, 6 minus 1. The question is, which one has the largest standard deviation? Now remember what a standard deviation measures. It gives you a measure of how far the data points are from the mean. If the data points are all close to the mean, the deviation is going to be small. If the data points are far from the mean, the deviation is going to be large. So based upon these three graphs, which one do you think has the largest standard deviation? Which one? Say again, sorry? I didn't hear you.
I was asking if you said the data, if it was far from the mean, the deviation was...
Would be large because the further things are from the mean, the greater the deviation, and therefore when you square it, the greater the squared deviation. So it is a larger contribution to this formula, this standard deviation. So which of these data points, how do I get my thing back here? Hold on. Here we go. Which of these data points seems to have data which is furthest from the mean? So Yesenia, I think it was,
A.
guessed B with 2 question marks.
I say B too because of this. There's such a range. No.
They all have the same range. The range is not the determining factor. The determining factor is which one has most of its data points far from the mean.
A.
A.
Most
has
of the data
tons.
points far from the mean.
A has tons over here at 1 and 6 and not so many here near the mean. Okay, so A is going to have the largest standard deviation. Which one's going to have the smallest standard deviation?
C.
I don't know. I don't think about that. Which one has
B.
most of its data points near the mean?
B.
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 No, B.
B.
Yeah, B has most of them
That's
near
what
the
they
mean.
said.
Right? Oh, I'm sorry. I thought you said C. B has most of them near the mean and very few of them on the wings. C is kind of like somewhere in between, right? It's got a lot close, a lot far, so it's going to be somewhere in between. I mean, without actual numbers, I can always compute them. I know the frequency of each. I can, in theory, compute the deviations, but that's really annoying. Then again, my calculator can do it, but in the interest of time, we're not going to because they're not asking us to. So this is the idea, okay? Conceptually, without doing the math, you can get an idea of relative magnitudes of standard deviations just by looking at the graphs, okay? So finally, the last section, compare the measures of variability. So you have learned 3 ways to measure the variability: the IQR, the MAD, and the deviation, the standard deviation. Often, but not always, when comparing distributions, each of these measures will give the same answer. And therefore, who cares which one you use? However, there are times that you will get different answers. And in those situations, some of them are better than others. So generally, the IQR is the most useful when the distribution is strongly skewed or has outliers, okay? If the distribution is strongly skewed or has outliers, then you want to use the IQR as your measure of variability, okay? The standard deviation is the most commonly reported measure. It has important mathematical properties and is most useful with symmetric distributions. What does symmetric mean? Again, it means if you basically look at the center of the graph, does it kind of mirror itself on both sides? Okay, is it symmetric versus skewed one way or the other? The MAD is used mainly to introduce the idea of deviation, but is never actually used, right? Nobody ever uses the MAD in real life. There's no nice mathematical properties like there is for the standard deviation and the IQR. Now, what can you conclude if the MAD is 0? You can conclude that all data points are equal. The only way that the MAD can be 0 is if all data points are equal. In that case, everything is equal to the mean, and therefore there is no deviations. All data points are equal. What can you conclude if the standard deviation is 0? The same thing. Because again, you're computing deviations, you're squaring them, you're adding them. How do you get 0? Only if they're all 0. But this one's a little more complicated. What can you conclude if the IQR is 0? What can you conclude if the interquartile range is 0? Remember what the interquartile range is? That means it's Q3 minus Q1, correct? Yes? Anyone? Bueller?
Yes.
Anyone there? So if the Q3 minus Q1 is 0, that just means that the middle 50% are all equal. The middle 50% are equal. So that Q3 is equal to Q1 and the IQR is 0. But the outside 50% could really be anything, as long as the middle 50% is equal to 0. ¿Verdad? ¿Comprende? ¿Entiende?
Yes.
Understands? Good.
What would that last one look like? Middle 50% are equal. Is that like C? Not really. No.
No, with C, none of them are equal, right? You have 1s, 2s, 3s, 4s, 5s, 6s. You got them all over the place. It would look something like this. It would look something like this, like So basically, you know, something, maybe you'll have a couple things like this. Right, so you have, this could even be skewed here. And maybe this is, you know, taller like this or something. But basically you'll have Q1 right there. And Q3, right? These are both the same location right here. It's Q1 and Q3. And then here's the first 25%, here's the last 25%, but the middle 50%, all the same value. You don't come across that often, but it does exist. Okay, so I just wanted to finish that quickly because it's really important that we move on to the next chapter right now. Okay, so let me load up. Chapter 14 on the normal model. This is muy importante, the normal model. Okay, you all with me? You all see it? Yes, no, maybe so?
Yes.
Okay.
Yep.
All right, but I lost all of you. Where did everyone go? How do I get everyone back? Okay, there we go. Okay. So we have the normal model. The normal model is, without question, the most important distribution in statistics. Okay, for two reasons. One, in terms of occurrence, the normal model occurs all over the place in nature. And two, even distributions that are not normal, it's going to turn out, become normal. I want to give you an example. This is a little ahead of what we're doing. The applet for central limit theorem. So you can all see this this thing here. So this is a distribution that comes from a normal distribution. Okay, it's got a nice bell curve shape. If I increase the sample size, it might get a little skinnier, but essentially it's still a normal distribution. Okay, as the sample size goes up, the distribution does not really change shape. But let's look at something that's very, very not normal. This is extremely skewed. Which way is this skewed?
Right.
It's skewed to the right. Okay, so if I increase the sample size to 2, it's still skewed to the right, correct? If I increase it to 3, 4, 5, what's happening as the sample size gets larger?
It's getting steeper.
Well, it's not the steepness that matters, it's the shape that we're talking about. What's happening to the shape as the sample size goes up?
It starts to become normal.
It becomes normal. Here's one that's very not normal looking, correct? Sample size 2, sample size 3, sample size 4, sample size 5, skip to 10. What do we see? What's happening? It's becoming normal. Doesn't make a difference what the initial shape is. If the sample size is large enough, it starts to look normal in ways that we will become more mathematically precise as we go on. The point I'm trying to make here is that the normal distribution pops up all over the place, and it's extremely, extremely important. Okay? So many medical tests and tests of intellectual ability or achievement have scores that are normally distributed. For example, the plot below shows the SAT scores, verbal plus math, received in 2013 by high school seniors. The shape of this distribution is approximately normal. It's not exactly normal. There's bumps and whatnot, and it's a little skewed to the right, right? You can see on the right, it's a little bit of a tail on the right versus the left, but it's approximately normal. The mean and the standard deviation typically are used as summary statistics for a normal distribution. These scores have a mean of 1,011 and a standard deviation of 216. Now we're going to use those numbers for a lot of examples today. Do you see why the mean is 1,011? Yeah, where's the balance point for this distribution? Where would you put your finger underneath it for it to be in balance? Roughly where?
1,000.
About 1,000, right? So they're telling me that it's actually 1,011, but certainly roughly in this area somewhere, correct? The question is, how do they get that? Now the answer is they did the formula. But can we look at the graph and come up with a value close to here? And the answer is yes. So let me show you how. I'm going to trace out the distribution. Crap. Try that again. I'm going to trace out the approximate distribution here. Okay, approximately. Now the mean is roughly right here in the center. Okay, with me so far?
Yes.
Now, there's two basic shapes that we're going to consider, an upside down U and a right side up U. Would you say in this area of the graph, it looks more like an upside down U or more like a right side up U? In this area?
Upside down.
Certainly upside down, right? Correct?
Yeah.
And here in the wings, would you say it looks more like an upside down U or a right side up U?
Right side up
Right
U.
side up.
Right? It looks more right side up. It might not be the entire U, but it certainly looks that way, correct? So somewhere the graph changes from being upside down to right side up. Roughly where is that location going to be?
Either 400 or 1,550.
You mean over here? This is the location where it changes from being upside down. I'm looking for the
More
point.
like
At
1,300.
So about here or so?
Yeah.
And about here, would you guys agree with that roughly?
Yeah.
Well, how far is this distance?
Do you add all of them and divide by
No. Just how far is it from here to there?
About 350.
Okay, so if we did it correctly, it would be 216. Okay, the distance from the center to where it switches is the standard deviation. So as such, I'm going to pick a value a little higher up, just so that my graph is better. This distance here, or this distance here, is the standard deviation. So if I go directly from the center to the point where it switches from being right side up to upside down, that distance is called the standard deviation. Now, in calculus, we have a name for that point. It is called an inflection point. You don't need to know that, but just know that this idea that I'm talking about is not just, oh yeah, it's over there. There's a very precise mathematical way of finding that point so that two people don't say, well, I think it's there. Well, I think it's there. No, there's an exact spot. But this is the graphical way of getting an idea of the standard deviation. Okay, but nevertheless, we have a formula, or they're going to give it to us, both of which are very, very nice of them. Okay, now here's the important part of the normal distribution. The mean is right here in the center. I'm going to try to draw a straight line. I'm getting better at straight lines. How's that? Is that a good straight line?
Yes, it's beautiful.
Well, thank you.
Excellent.
Thank you. I've been working really hard on that.
Can
Now,
tell.
thank you. Thank you. Thank you. Now, if I go to the right, to the point where it flips from being an upside down U to a right side up U, that would be roughly here. That seemed like a reasonable point.
Yes.
Okay, and it's corresponding over here.
Mm-hmm.
So that is one deviation, one standard deviation left, and one standard deviation right. The question is, how much of the data falls in this region of one standard deviation left to one standard deviation right? And I just want to stop here for a second because this class is too boring without Angela making some kind of comment sometime. So I'm going to stop for her to say something, or at least type something, because this is just like way too serious. And
She's softly quiet.
I'm just not having a good time right now. So Angela, come on, say something. Do something. Okay, I'll take it.
Oh.
Okay. So how much of the data falls between those 2 points? So this is a fact that you're not going to just guess. Well, you might. You might. I mean, it's obviously not all the data because we still have the stuff here and we still have the stuff here. So if you had to give a guess for how much of the data falls between one deviation left and one deviation right, what value would you assign to that?
50?
Okay, 50% is a pretty good guess. It actually
75. No.
That's a better guess. It actually ends up being 68% of the data for a normal distribution is between one deviation to the left and one deviation to the right of the mean. That's just
All the time.
all the time. That is just a fact. Now, if I were to go to 2 deviations left and 2 deviations right, so now I'm including not just the middle 68%, but also a little bit more. It's still not 100%, obviously, because I'm still missing some. But if you had to guess as to how much falls within 2 deviations left to 2 deviations right, someone make a guess.
90.
Patty, she turned what? She turned 19, and that's not good? What are you talking about? 19's a great age. Everyone wish Angela a happy birthday. She turned 19 sometimes recently. I just don't know when.
Happy birthday,
Happy
Angela.
birthday.
When was your birthday, Angela?
It was Sunday.
It was on Sunday.
Oh my God, that's the day after
Did
my
you have a
birthday.
nice
Happy
party?
birthday to you. Happy birthday to you.
Happy
Happy birthday, dear Angela.
Angela.
Happy birthday to you.
So thank you for all the tone deaf people who sang. I really appreciate that. That was wonderful to hear.
I was on Thank you.
Okay, well, Angela, happy birthday and many more.
Yeah.
Thank you.
And I'm just glad that you were able to be in my class during your birthday week for a real celebration amongst your peers.
Yes.
Thank you. That really meant a lot to me.
You're welcome. Now, Angela, answer this question. How much is between 2 deviations left and 2 deviations right? And I'll give you a hint,
I'm
Angela.
gonna pull my birthday pass on this one and pass it over to Patty.
Unfortunately, I'll give you a hint, Angela. How's that? It's literally written on the page what the answer
I would say something like a number 68.
No, 68 is one deviation. We're going all the way to 2 deviations.
Got it. I would say something like 99.7.
Oh, because you saw that on the page? Oh, but unfortunately you're reading the wrong one.
I would say something like
95.
95, that was a great job, yes.
Thank you.
How on earth did you figure that one out? That's amazing.
Oh, excuse me.
Honestly,
Bless you.
Thank you. Sorry, I was trying to mute myself. Didn't get there in time.
Patty
It's okay.
and Angela, you guys are amazing friends. You guys should work out whatever your issues are because that just is horrible. So I say fix it because you guys are awesome friends.
Wait, time out from math. Group therapy. Sounds like we need some group therapy.
Yeah, unfortunately, that might take too long. So we're gonna have to postpone that. I'm just saying in general, you should definitely work it out because life is short, play hard, that kind of thing.
You
But-
can mesmerize them to get back together with your blue eyes to be best friends again.
Yeah, if that worked, I'd be doing a lot more with it. But anyway, so again, what if I go to 3 deviations out? What if I go all the way to 3 deviations out in both directions? What percent of my data falls within 3 deviations?
99.7.
99.7%. So almost all of the data is within 3 deviations on either side of the mean.
So
Okay.
what would we write on the bottom when it says 90% of newborns' lengths are between blank and blank?
Well, I haven't got there yet. 1 second. And Henry, you're entirely correct. Orange creamsicles fix everything. That's right. Okay. So we have 3 numbers that are important to know. The numbers are 68%, 95%, and 99.7%. Okay. These numbers mean so much when it comes to normal distributions. If you go 1 deviation from the mean in either direction, 68% of the data, approximately. If you go 2 deviations in either direction, 95% of the data, approximately. And if you go 3 deviations in either direction, you get 99.7%, approximately. Now, you'll sometimes hear the words almost all values. When you see almost all values, that's synonymous with 3 deviations to the left and 3 deviations to the right. Okay, so almost all, that's exactly what it means when you see the words almost all, 3 deviations left and 3 deviations right. Now, what we're going to do now is put this into practice so we can, answer the questions on the bottom of the page. It says the lengths of full-term newborn babies are normally distributed with a mean of 20.5 inches and a standard deviation of 1 inch. So what would the value be right here in the middle? How many inches is the center of my graph going to be?
Do we subtract 20.5 from 1.0?
No, don't subtract anything. It's immediate. The center of the graph is what number?
0,
0.
1,
Not 0.
1.
These are all babies. Do babies have a height of 0 when they're born?
Is it 10?
Where do you get 10 from?
20.5?
Or 0.5.
2.5, the mean.
Oh,
Remember, the mean is the tipping point. The mean is the balance point. For a normal distribution, the mean is right in the center at 20.5. Now, if I go 1 deviation to the right, what's it going to be here?
68.
No. 68%
One?
is how much?
1?
No, this is 21.5. And if I go 2
Oh.
deviations to the right, what's this one going to be?
22.5?
22.5. And if I go 3 deviations to the right, what's this one going to be?
23.5.
23.5. If I go back to the mean and I go 1 deviation to the left, what's that going to be?
19.5.
19.5.
19.5. And if I go one more to the left, what's that going to be?
18.
18.5.
And if I go one more to the left, what's that going to be?
Why
17.
17.5?
So almost all babies that are born full term, almost all babies are between what two heights?
17.5 and 22.5.
Excellent. 17.5 and 22.5. But that's not
What
they're
is
asking.
math baby, I wonder?
What is what?
What's math baby?
What is math baby?
Oh,
How
how
big is Liam? Or
oh,
how
how
tall?
big is Liam?
Oh, Liam
He
baby.
is, when he was born, he was 15, but now
Oh.
he's big. He's
Wait,
22,
Was he
23.
born full term?
Yeah.
Oh, he was little.
So
Yeah, he was born 5 pounds and 8 ounces.
Wow.
yeah, I don't know what these things mean. But anyways, that
Sorry,
means
Professor.
that your baby was exceptional.
It's because of me.
Well, that could be too. But your baby is exceptional because almost all babies are born between 17.5 inches and 22.5 inches. And your baby was past that. So that means your baby is unusual. Well, more than unusual, exceptional. Okay. Now, 95% of newborn babies are between what two lengths? Not almost all, but 95% are between what two lengths?
17.5.
17.5.
Not almost all.
18.5, 22.5.
18.5 and 22.5. Because remember, 95% are within 2 deviations of the mean.
Okay.
So that means you go to the mean and you go 2 deviations left and 2 deviations right. Crystal Flores, what did you just type in?
They're talking about the soda, okay? Leave them alone.
No, she said, ooh, orange creamsicles. That's what she said.
Seriously, gross.
They're so.
Okay. I'm gonna let this one go. So how do you know it's an ooh if you never had one? You crossed the line. She crossed the line.
FYI, Zevia has cream soda. Cream soda.
No. Orange creamsicles are just extremely wonderful. Oh, great. Woo! And I'm sorry, I take it back. You're all liars. Okay, here again is the distribution of total SAT scores, which has a mean of 1,011 and a standard deviation of 216. Complete a simplified scale for the scores using only the mean and the standard deviation. So what number goes directly in the center?
9.
No.
1,011.
1,011. They told me
I
what the
can't
mean was.
see.
You can't see? Check your eyes. What's wrong with your eyes?
It's just so small.
What is exactly?
Well, that's not you, it's me.
Oh, okay. I've heard that before.
She does wear glasses. That was kind of a
I
low
know.
blow, Professor.
Doesn't mean anything.
Okay, well, I'm sorry. So, okay, so 1,011 is the mean. Now, if I go 1 deviation to the right about here, then what value do I get?
1170?
Try again.
1100? No,
Try
you have
again.
1100. Sorry.
There's no guessing here. The math is in front of us.
1,227.
1,227. Can you explain where that came from?
I
Add
added 1,011 plus 216 because the
Yeah.
standard deviation is 216.
Excellent. You take the mean, which they gave you, and you add it to the standard deviation, which they gave you, and you get 1227. If I go another one out, what do I get now?
Add another 216.
Add another 216.
1443.
1443. If I go another one out, what do I have now?
1659.
1659. And if I go back to the mean, but this time go down 1 deviation,
minus 216 is
795.
795. And if I go another deviation down,
580.
5, that can't be right.
579.
579 makes more sense. And if I go one more deviation down,
363.
363. So that's my scale. So almost all scores are between what two values?
216? No, 363 and 169, 59.
Good. Now 95% of them are between what two values?
579.
79 and 1,443.
Excellent. So we actually already answered this one too. Almost all between 363 and 1659. Does that make sense so
That-
far?
All?
Professor, what grade is this? This is beginning statistics, right? In school, what grade is this for?
You mean what grade would you be teaching that would cover this?
Yeah, do you know?
High
don't-
school?
Is it high school?
I learned this in high school, so I'm assuming.
Oh, okay.
I
Like-
don't have an answer. I don't have an answer for you. I don't know that. I don't know the answer to that.
Like 9th grade high school? Or?
No, it would be
I took it senior year.
Oh, okay.
11 or 12th graders.
I see. Okay. Sorry.
I thought you taught high school math, Professor Berkowitz.
I do, but not this.
Oh.
Not statistics. So
What do you teach in high school? Algebra?
algebra, trigonometry, geometry.
I hate geometry. Oh.
Is also a Gen Z thing for
For amazing.
I can't. I'm trying to think of like OGH, what that might stand for. Ultra great, exactly. Ultra great. That must be what it is. All right. Okay, so example. A total SAT score of, say, 1230 can be meaningless to many students. So a measure of position, such as a percentile, also is recorded. A total SAT score of 1230 places a student at about the 85th percentile. Locate this score in the plot above. Well, let's go to the plot above. The 84th percentile means that 84% of the data is beneath it. Approximately, where would 84% of the data be beneath? So let's think about that, shall we? We know that if I go one deviation to the left and one deviation to the right, how much of the data is in that section?
68%.
68.
68%. Which means how much is left over for the sides?
99.
1 second. The whole thing is 100%.
32.
32% is left over, correct?
Mm-hmm.
How much of that 32 is in this area and how much of that 32 is in this area?
The second one?
16.
16 and 16.
16 and 16, right? Which means if I score in the 84th percentile, that means 84% of my data is going to be beneath me. What location on my graph has 84% of the data beneath me?
The left side of the graph?
No, what point exactly? What score has 84% of the data beneath it?
363 through 1227.
Wait, again, I'm looking for one score that I say 84% of people scored less than me.
1230.
So according to what they just said here, it should be 1230. Does that jive with what you see in the graph?
So will
Yeah.
will that be between 1,227 and 1,443?
No. Just look at this one score, 1230 right here.
Yes, it does.
How much is left of it? It's all of that. All that 68% and that 16% is
16%.
left, which is how much?
84%.
84%.
Magic.
So we see that a score of 1227 or approximately 1230 does in fact give 84% of the data to the left of it. Does that make sense? Because I have this 68 plus this 16, that's a total of 84%. Yes?
Yeah.
Okay. Now, it's going to get a little more complicated. Have no fear. Okay. Now, when you score in the 84th percentile, does this mean that the student got 84% of the questions correct?
No.
No.
What does scoring in the 84th percentile mean?
That they did not do well.
No, they did very well. They did very well. What does scoring in the 84th percentile mean?
They did good.
Be more specific, please.
84% of the people taking the test scored in the higher range.
Oh, you were
or-
doing so amazing until the end. Oh,
Oh,
you were doing perfect. I had my hands up for a touchdown.
Scored less.
And then,
it was like the last play at that game on Saturday night,
what game?
the Dodger game.
Oh, yeah.
Yeah, but I heard they won the next one. So they're
Well,
all,
then they did win the next one.
is it over? Did they win the whole thing?
No,
No, tonight.
they have 2 more games if they don't win today.
Okay, so I was
Yeah, Hasmi got it. Hasmi got it. You did better than 84% of the people.
wait, say that again.
I don't have to. She did.
Oh.
Hasmi, look at her
Let me
text.
go back and read the chat.
Sure, okay. They're winning.
Yes, they're
tonight,
winning.
y'all. They're winning
Absolutely,
tonight,
Angela.
Y'all.
Better win, Dodgers. You
Y'all.
did better than 84% of the people. I'm having a hard time wrapping my head around that. Wait a minute.
If you score in the 84th percentile, that means 84% of the people did worse than you.
Oh, okay. Let me, if my baby was born in the 84th percentile, he's like a big baby.
He's taller
Bigger than,
yeah, he's taller than 84% of other babies that are born under the same conditions. That's correct.
okay.
What about the babies, or what about the people that are above 84%? What if they're like 90%?
Then
Than
they're
90%.
better than 90%.
Better.
I took a test a couple years ago. I scored in the 90th percentile. I was really happy with that score.
So whenever we want to express that an individual did better than a certain percent, we give the percentile of.
Yes.
Okay.
Yes, 100%. That's exactly what a percentile gives you. And it's not just for scoring, it's for heights as well. Babies, it's for weights. My niece was very short for her age. And her percentile was like the 10th percentile. Now, what is the usefulness of knowing that?
Bragging rights.
No, not bragging rights. You don't brag that, hey, look, I'm below average. No, people don't do that. Right? You might brag that you're above average, but very rarely do you brag that you're below average, unless, of course, you're playing golf. Like, my score is below average. That's good. Okay, but for most things, you don't do that, right? So in my niece's case, because her percentile was so low, they were worried that something might be wrong with her physiologically. So they took her in, and sure enough, she had Crohn's disease, which is something that affects your growth hormones, I guess. I don't really know the details. But, knowing the percentile could lead to treatments, could lead to, corrections. Whereas if you don't analyze the data, then how would you know that there's anything that there's an issue anywhere? Does that make sense? I hope so. I don't know if everyone
Yeah, it makes sense.
stop paying attention there. Anyways, what is the percentile for a score of 1,011? What is the percentile for a score of 1,011? Let's take a look. Let's find 1,011.
68th
There.
percentile?
Yeah, 68th
Nope.
percentile.
Nope. What's a percentile for 1,011?
Oh,
84?
50.
50. You're right in the
Oh
middle.
yeah, that's right. 50.
Right? You're right in the middle at 1,011. 50% are beneath you. 50% are above you. Okay. So I'm going to skip the next question because it's not important. And let's move on to next. When tests are normally distributed, two other measures of position often are used, what are called the z-scores and the t-scores. So we're going to start with z-scores right now. Z-scores are an extremely, extremely, extremely important aspect of statistics. Right? A z-score is the number of standard deviations a score falls from the mean. I don't care what the mean is. I don't care what your score is. What I care about is how far you are from the mean in terms of standard deviations. So here's what I mean by that. According to this distribution right here, this normal distribution, what is the mean?
100.
100. What is the standard deviation according to this distribution?
15.
15. Lori, you are on fire tonight.
I show signs of intelligence every once in a while. I will,
Correct.
once in a while.
And when you do, I like to point it out. That's all I'm saying.
Okay, thanks.
Now, if you scored a 115, what would your z-score be?
I just learned what z-scores are. Wait a minute.
Congratulations.
85.
No. I guess you didn't learn. What is your z-score if you score a 115 in this situation?
Positive?
But positive what? How many standard deviations are you above the mean?
Is it 1?
1. You are 1 standard deviation above the mean. And if you scored a 70, what is your z-score?
-2?
-2, because you
Wow,
are
you guys are on fire.
Well, someone has to be, right? Right?
See.
So, if you're at 100, how many deviations are you above or beneath the mean?
0?
None.
So your z-score is 0. What about 110?
0.75?
110.
Quite 0.75.
0.5.
Not quite 0.5.
Crickets.
Crickets.
15?
You're 15 deviations above the mean. So I'm going to go 15 deviations above the mean. Is that where 110 is? A deviation is 15, right?
Oh, so half of that.
Not half.
0.10?
0.66?
Close. 0.6 bar, yeah. 2/3. Right? You are 2/3
Oh.
of a deviation above the mean.
All right.
Right? Every deviation is 15. So if you are 110, you're 2/3 of a deviation, correct?
See.
C.
Hi.
Hi. Oh, thank you. Were you hiing my father?
Yes.
Hi. He hies back.
Is he a math professor too?
No, but he knows one or two things about math. Literally.
So he's the one who taught you how to teach math.
No. I'm still learning. So, every day is a learning experience.
As it should be.
Right, Angela? Yeah. If we're not getting better, then we're getting worse. I just made that up, but it sounds so profound. Anyways, z-scores. Okay, there's actually a formula for z-scores. I do treasure them.
Of course there is.
Of course there is. So what is the formula for z-scores? Well, it's right there. You take your data point, x, you subtract the mean, x bar, and then you divide by the standard deviation. You want to do a treasure hunt? Like, what does that mean exactly?
That's a great distance learning thing.
Yeah, we should all
Good
get
idea.
together at a park and do.
Also, we never did show and tell. That's true. That's on the agenda. Okay. So let's go ahead and compute the z-score for 1500.
Okay, so 1500 minus
A costume party.
What mean are we using? Are we using the mean that we were using before?
Yeah, yeah, because it's the SAT score example.
Okay.
So what was the mean for the SAT scores?
it was points 2/3, which is points.
No. What's the mean for the SAT scores?
1,100.
1,011.
Oh,
What was the standard deviation for Thursday's Halloween?
No, Halloween's on Saturday.
Halloween's on
Oh,
Saturday. So you want to have
this,
a costume party on Thursday during class.
that's awesome.
yes, we can all order pizza and eat it together. Except you. You have to eat carrots and celery.
No, I don't have carrots and celery. I have cucumbers. That's my compromise.
Oh, my favorite.
The
I
Persian
love
cucumbers?
No, regular cucumbers. What do you mean?
I
Oh,
love
you're missing
cucumbers.
out on life.
Cucumbers don't have a nationality. They're just
Yes, they do.
There's English, there's Persian, there's
Oh my God, do you know what Super
Minnesotan.
King is?
Yes, I go there all the time. It's on the block from my house.
Okay, go get Armenian or Persian cucumbers. You'll love them better. More.
Okay, I will try it. Yeah, Super King is literally, I can see it from my house. That's how close I am.
So the SD is 15. I'm sorry.
Not 15. Was it 15 for the SAT example?
I think it was 216.
The SAT example was 15, right?
100, no?
No,
The
that's
standard deviation
Right here.
Oh,
of
it's 216.
216.
Thank you.
So we
Pages.
divide by 216. So what's my z-score?
2.26.
Okay, I'm not doing the math, but I'll trust you. 2.26. See, Yesenia, I trust others. 2.26. So that means, would you say that this z-score is unusual? So the answer is yes. The general rule for the word unusual is more than 2 deviations away from the mean in either direction. So if you get a score above 2 or beneath -2, if your z-score is past 2 or -2, we say that it is an unusual score.
That's where like the tail ends, right? Where it's almost to back to the line. To the
Yeah,
X.
I mean, they're still past that because you can still get to the almost all, which is 99.7%. But once you go past 2 deviations, we say it's unusual.
Okay.
So scoring 1500 is unusual. What about 940? What's the z-score for 940?
I got -0.32.
Okay, -0.32. Is that unusual?
Do you still do the, oh yeah, -10, sorry.
Actually,
be-
put 33 because it's -0.328.
Okay, so there's 0.33. Easily fixed.
Negative?
Negative, because you're beneath the mean.
No.
Yes, the mean's 1,011 and you're at 940. How are you not beneath it?
Oh. Oh, now I'm confused again.
What's wrong? 940 is to the left of the mean, isn't it?
You said that if we are past -2 or +2, then we are in an unusual, right? That's
Well,
what
we use this, we would say it's an unusual result, correct?
right. This is not past that.
So it's not unusual.
So that's what I'm saying.
Yeah, but it's still negative.
So it's unusual.
I'm so confused.
No. Negative doesn't mean unusual.
Oh, okay.
Negative just means beneath the mean.
Just
Two.
beneath me.
A -2.
Past
Oh,
two
unusual.
deviations. Didn't you say unusual means past two deviations?
Yeah, so you're past 2 this way and you're past -2 that way.
Okay, so basically, if we're answering the question, the example, it is below the score, right? That's what the question is asking.
Well, the question says compute and interpret the z-score for each SAT total score below. For 1500, the z-score is 2.26. For 940, the z-score is -0.33.
Right.
This means that 1500 scores 2.25 deviations above the mean. And 940 is a third of a deviation below the mean. Right? -0.33. 0.33 is about a third, right?
Right.
So that means you're 1/3 deviation below the mean. So on the distribution, oh, Jesus. That's horrible.
It's better than some.
Thanks. So if here's the mean, and here's 1 deviation down, 940 scores about there.
Right.
That's really close to the mean. That's not unusual at all. But 1500
There's 2.
scores there. That's more than 2 deviations from the mean. That's unusual.
Okay, see that I get. Visuals I get. You need to draw it out.
Oh, I need to? Oh,
Yeah.
Yes, you need to. You want me to get this or not?
I really don't care.
It's all on you, Professor.
Meanie
Right.
pants.
It's
Meanie.
all on me. Maybe there's a picture on the next page. No, there isn't. But here, you want a
Wait,
Oh,
visual?
look, it's the
Listen.
Kardashians.
Vote for
There's-
Kanye.
Kim and
Whoop, whoop.
Kanye. So 2 paragons of intelligence and
Okay, I never realized she was that short.
Professor, are you gonna vote?
is she that short? That's the question. So let's take a look.
No, she's
Kim is-
wearing heels.
Kim is 5 feet 2.5 inches tall, and Kanye is 5 feet 8 inches tall. Now, men in general have an average of 70 inches, with a standard deviation of 3 inches, and women are in general 65 inches. That's their average, with a standard deviation of 2.6 inches. And the question is either one unusually short? How do I determine if am I going to vote? That's none of your business. Am I going to vote? But the answer is no, I don't vote. But anyways, is either one unusually short? And when we say is either one unusually short, what we mean is when we compute their z-scores, does either one have a z-score that's beyond 2 or -2? So let's compute the z-score for Kim. What is Kim's z-score? Well, what's her score? What's her height?
70.
No, where do you get that?
I'm sorry,
That's the mean.
65.
No, that's not
Yeah.
true either.
Oh,
She's
5.2
5'2".
and a
Wait.
half.
Wait, you're sending a, why are you calculating if you fit the average? What does that mean?
Because you were doing the math, you were like counting on your fingers and counting in your head. When you read that for men, it's 70.
I was figuring out what 70 inches was.
Oh, okay.
Oh, do we have to make the 5.2 and a half to inches?
Inches.
Yes, you do.
Like 46 and some change, 47.
Well, okay, so your math is a little off there.
No, 5 times 12 is what?
Isn't it like about
60. Oh,
60.5?
5?
62.5.
What's the average
65.
and what's the deviation?
It's 2.6?
So what is Kim's z-score?
Negative
have my-
0.96.
Negative 0.96. Is Kim unusually short?
No.
No, she's short. She's one deviation down approximately, but she's not unusually short. Now, what's Kanye's z-score?
So Kanye is 5 times 12. 5 times 12 equals 60 inches, 68 inches.
Okay.
68 inches
Minus
minus 70
70.
No, I did it wrong.
divided by
3.3.
2.6 equals,
2.6.
oh, sorry. It's late in the afternoon.
Oh, I understand. Yeah, 3:14, really late.
Well, when you've been up since dark 100.
Oh, dark 100. Nobody gets up at dark 100.
Yes, I do.
Why would anyone get up? No, you don't get up before the sun comes out. That's a rule. All right.
That's
Anyone
Don't
does
forget
So-
to change your clocks this weekend, by the way.
Thanks,
crap.
Lori.
Wait, are we getting an hour or losing an hour?
Getting
We're
an hour.
gaining.
Okay, I can handle that. I'm okay with that. Let's do it. We should do it every week.
Thanks, Lori.
You're welcome, everybody.
Professor.
I'll
I'm
take
happy
it.
about that
B.
extra hour.
Huh?
So for B, women are
Wait. So the question is, who is taller compared to others of their gender? Kim
Who
or
is
Kanye?
taller compared to others of their
Kim.
gender? Wait a minute.
I will wait 2 minutes.
Kim.
Oh, wait, it's 3:15. I can't wait 2 minutes. Who is taller? The answer is Kanye is taller because he is closer. He's further to the right on his distribution than she is. He's only 2/3 of a deviation down, and she's a full deviation down. So Kanye is taller.
But 5'8" doesn't seem that tall.
It's not. It's still a deviation down, but it's taller compared to men than Kim is compared to women. So we will stop here at the end of page 7.
Okay.
And we will continue this next time. And the quiz on section 11 will be up. And just get it done when you can, if you don't mind. And Angela, I want you to smile more. Okay? You're so much better class when you're smiling. And
Yeah,
you're so
I'm
much happier when you're
contributing.
smiling. So I don't know why you're sad, but I don't like it. And I want you to stop right now.
Professor, so when is quiz 5 due?
Okay, good. Quiz 5 is due. I'll give you a week. What the hell?
Over the weekend?
All right, have it due by next Tuesday. Okay.
Yay, Professor.
Woohoo!
Angela's the best. Everyone say Angela's the best.
Of course.
Angela
You're
is the best.
Rock, my queen.
Okay, except for Celeste dog, because my God, that dog is so cute. So Angela's really second best. Wow, look at
Of
that.
the two-legged.
So adorable. Huh?
Of the two-legged.
Of the two.
But
yeah,
that
the two
dog-
ones.
That dog is cute.
Yeah. All right. Anyways, get lost, everyone. And I will see you guys.
Enjoy your week.
All right. See you on
Enjoy your
Bye,
week.
everybody.
Bye. Good luck on your diet.
Thank you.
Bye.
I miss you.
Oh, thank you. Oh my God.
Sorry I was late to class today. I was having internet issues because of the
Okay.
wind.
How late were you?
Like 10 minutes, something
Okay.
like
So
that.
I have to mark you late. I hope you understand.
It's
but-
okay. I get
But
it.
but with that dog, so cute though. You're better off. Oh, hello. Hello. Oh, it's adorable. All right, sounds good. Okay.
Thank
You're
you.
welcome. I'll see you later, okay?
Bye.
Okay, bye. Jose, you have a question or you're just waiting around or you're just not really there but pretending?